You know, modern engineering simulations create these absolute mountains of data. But here's the thing, all that data is completely useless if we can't make any sense of it. So today, we're going to go on a little journey, starting with raw numbers and ending with real insight. We're going to explore how we make the invisible visible.
So let me ask you something. How do you see the wind? I mean, you can't, right? You can only see what it does. For an automotive engineer, that's a massive problem. They need to literally see how air is flowing over a car to make it more efficient. And that's exactly what we're going to do today. We're going to see the wind. And it all begins right here with just a single data file. This one is called Kit-CAE_sample.cgns. Inside this file is a virtual car and all the results from a super complex simulation. But right now, it's just a huge mess of numbers. Our job is to turn all this digital noise into something we can actually look at and, understand. Okay, before they get to the really cool visuals, we have to set the stage. This first part is all about prepping our data. And trust me, if we get this wrong, nothing else is going to work. The whole setup really just boils down to 3 simple steps: import, scale, and orient. First, we bring the data into our software. Then we make sure it's the right size. And finally, we get it sitting upright in our virtual world. Easy enough, right? Now that scaling step, it might seem like a tiny detail, but it is way more important than it looks. See, the simulation was calculated in meters, but our software thinks in centimeters. So we've got to scale everything up by a factor of 100. It's the difference between looking at a little toy car and the real deal. Then a quick rotation and whoop, it's sitting perfectly. All right, our data is prepped and ready to go. Now for the fun part. Let's bring this car to life. So the very first thing we can do is create what's called a point cloud. The software basically puts a tiny little dot at every single data point from the simulation, and what we get is this ghostly outline of the car. But we can do way more than just stare at a bunch of dots. We can color each one of those dots based on the simulation data. In this case, we're coloring them by something called wall shear stress, which is really just a fancy way of saying we're measuring the friction between the air and the car's skin. Suddenly, we can see exactly where the air is dragging on the car the most. A point cloud is pretty cool, but let's be honest, we want to see a solid car. So the next logical step is to connect all those dots. The software stretches this kind of digital skin over the entire point cloud, turning our ghost into a solid object. And boom, you can see the difference right here. The point cloud on the left shows us the raw data points, but the solid surface gives us a much better feel for the car's actual shape. And now that it's solid, we can color it with different data. Here, we're using something called Y+. Now, this is a super important value that tells engineers how the turbulent air is behaving in that razor-thin layer right next to the car's skin. Okay, we've seen the car. That's great. But now for the main event. Let's finally see the wind. To actually see the wind, we're going to use a tool called a streamline. Just imagine a tiny weightless speck of dust getting caught in the airflow. A streamline is the exact path that little speck would take as it zooms around the car. So how do we make one? It's actually pretty cool. We just drop a little seed, in this case a small sphere, somewhere in the airflow. The software then looks at the velocity data and just traces the path of the air from that exact point. And the best part? It's totally interactive. We can grab that seed, move it around, and watch the airflow patterns change in real time. Now, streamlines are amazing for following one particular path, but they only show us a tiny piece of the puzzle. What if we want to see all of the air, everywhere around the car, all at the same time? For that, we need a technique called volume rendering. This is where things get really cool. It essentially turns all that invisible air into a transparent, colorful cloud. Now we can see the big picture. All the swirls and eddies and complex structures that we would have completely missed just by looking at streamlines. So we've made some incredible looking visuals. But here's the thing. These are not just pretty pictures. They are incredibly powerful tools. Let's take a look at how engineers actually use them to find and fix real-world problems. One of the most useful tools in the entire toolbox is the slice plane. It's like having a virtual scalpel. We can use it to slice right through the 3D data and see what's happening on the inside, from literally any angle we want. So an engineer could use a slice plane to see exactly how the air pressure changes over the hood, or check how fast the air is moving under the car. For example, they might see this giant red spot of high pressure right on the front grille. That insight is pure gold.
It tells them, hey, if we reshape this one area, we can reduce drag and make the car more fuel efficient. It turns a really complex 3D problem into a clear, simple, actionable insight. So let's take a quick step back and look at the whole journey we've been on, from totally invisible data to an incredible, actionable decision.
We started with nothing more than a file full of numbers. We turned it into a ghostly point cloud, then a solid surface. We watched the airflow with streamlines and volume rendering, and finally, we sliced it open to analyze what's happening on the inside. Every single step gave us a clearer and clearer picture.
And that right there, that's why this all matters. This isn't about making cool graphics for a presentation. It's about giving engineers the tools they need to understand the world in a new way, so they can build better, safer, and more efficient products for every single one of us. And think about it. These same tools can be used to see almost anything, from the way blood flows through our veins to the massive weather patterns that circle our entire planet. So the real question is, now that we can see any data, what invisible world are we going to explore next?